Hi, so yes, I am a human being, and today I'm going to talk about how we solve problems, right? And why we should use more diverse and varied notation when it comes to our data engineering problems. So my talk is going to be a bit different from the rest of the talk you've seen today, and I hope it does give you a bit of something to think about later on. What happens? Okay, so I'm a human being. You're a human being. We're all human beings, and the best thing about being a human being is not that we can solve problems. Many things in the world, living and non-living, can solve problems, right? The difference, the thing that makes us different as human beings is that we can solve problems, and then we can transmit our solutions to another human being via a long-lasting medium, right? So birds and monkeys and primates, they can do the same thing. They can transmit solutions to other birds, other primates, but their solutions are often ephemeral. Only we humans write things down, we make videos, and we document them for other human beings. So that's what my talk is all about. So let's talk about problem solving, right? So how do we solve problems? And as in general, we human beings have an algorithm for that, right? It goes something like this. We first simplify the problem, and we do this by simply breaking down the problem into smaller components. And this is actually very useful for the kinds of problems that are, well, 99% of the problems that are compositional in nature, and for the rest of the problems, we just solve a simpler version of that problem, right? And then the next thing we do is we solve the smaller problems. And the core of solving problems is that we are establishing the rules for how the elements of the problems can interact with one another, right? In the natural sciences, these rules are discovered, and in other cases, these rules are invented. And once we've done that, we solve recursively, and we combine the solutions upwards, and that's how we solve problems, right? So as a cultural species, you humans have expressed your mental states in long-lived mediums for millennia, and that's why we've got songs of love, you've got poems of joy, and paintings of depression, right? And problems are also mental states. And through the millennia, we have gathered a body of knowledge on how to represent these problems in forms of diagrams, equation, and code. What you see up here is something called a Wardley map, and it's very useful for exploring problem spaces. And on the left, you have the code representation of the Wardley map. And the code representation is mainly the work of my mate Olivier. And because the map is actually represented as code, it gives you, when you manipulate the code, it gives you more ideas on how to manipulate the map. And manipulation, I think, hints at the meat of this talk. Now, ultimately, there is a common unifying theme in the way we represent problems. When I said our ancestors managed to represent problems that in their brains out of their body, what I'm referring to is language. Now, language is very broad. So I want you to be a bit open-minded, right? When I say language, I don't mean Python, Java, or English and Mandarin. No. When I say language, I mean the structure, the things that you can describe with rules, right? Which we call grammars, and the elements of the problem, which we call vocabularies, right? These are all languages. So let me give you an example. In a database, you have a column that says the values in this column cannot be null. That's a rule. Right? And the values that actually go into the column, those are the vocabulary of the language, right? Your airflow DAGs are a language, right? But they're an unconstrained language. And if you don't constrain your airflow DAGs, what happens is you can have nodes that mutually depend on each other, and things explode. And this talk is mainly about written language. And when I say writing, I mean the whole spectrum of reading, and writing down the symbols, and manipulating your thoughts, essentially, manipulating your thoughts outside of your body. And this is vital because our brains are incredibly fast. When you are forcing yourself to manipulate your thoughts outside of your body, you're engaging in system 2 thinking. So, having explained the problem with problems, and let me just share with you what I've been roughly thinking about. It's my goal to build an AGI. So for the last 7 years or so, I have been thinking mainly about representing AI stuff in computers. And one of the various things that I've done is by writing Gorgonia. It's like TensorFlow or PyTorch, but it actually predates both TensorFlow and PyTorch, and it's written in Go. But really, it's more of an exploratory device for me to solve the kinds of problems that I want to solve. My question is very simple. Are there ways of writing down neural networks that can lend itself to a better understanding of intelligence? And speaking of neural networks, here are some ways we write our neural networks down. And spoiler alert, some are better than the others. To give you a taste of what this talk is about, let's look at the third notation. The third notation is written in something called Einstein's summation. Yes, that guy. See, Einstein invented a whole new language, and if you're a German reader, you'll note that he actually took it from Ritchie. But let's just say he invented the language, right? He invented a whole new language to express the way he thinks about linear algebra, and that led to the discovery of general relativity. And I'm showing you this because there is a very interesting trick that you can do on pen and paper with neural networks. Not really in computers, right? If you write your neural networks down in Einstein's summation on pen and paper and you manipulate your equations the way Einstein would think about linear algebra, you start spotting the weird optimizations that you can do, and you end up with a much faster neural network in the end. And all this by virtue of writing your neural network down in a slightly different way. Now, these are all rather mathematical notation. And from my experience dealing with humans, mathematical notation kind of scares people away. So the other thing that I've been doing is to represent neural networks in a form that is familiar and comfortable for software engineers. And so I did it by I started with a version of ML. And when I say ML, I mean Robin Milner's meta-language ML, not machine learning ML. If you're familiar with Haskell or Camel, this would look kind of familiar to you. And then I tried an algol-descendant language, which is like Go. I actually presented this as a generic version of Go before. And then finally, I built a surface language for Gorgonia that is essentially an APL. Who here has heard of APL? Wonderful. Now, other than the two people here, APL is a very, very, very old language. It's actually older than C. It's older than COBOL, right? And it's a bit weird because you use symbols, not words, to type, to code. And you write your APL code from left to right, but the machine executes it from right to left. So this on screen is the Conway's game of life. The generation step is the entire program is that line. Yeah. And this is the same example from the previous two examples, as the ML and algol version. And it's here I want to stop for a bit and do a deep dive into notation changing the way you think about a problem. So the APL that I developed is called Inigo. I meant to open source it before today, but things happened, so it will still eventually be open sourced. And you might notice it's styled a bit weirdly. That's because Inigo stands for Iverson notation in Go. I'll talk about this Iverson bloke in a bit. And when you have a language called Inigo, you clearly have to have an interpreter called Montoya who threatens to kill you, right? Right. A bit of history. I originally used Inigo as an exploratory vehicle for a better notation for differentiable programming, right? Then earlier this year, I sort of temporarily lost the use of my left arm. I couldn't type without the arm feeling like it was on fire or electricity going through it. So I thought to myself, hey, why not code in APL? Because you are going to be typing symbols, you're not going to be typing words, there'll be fewer things to type, less pain. So I got someone from Sri Lanka to help me finish the first version. And after using it a bit, what I discovered was that it changed the way I think about solving problems. So now that I can use my left arm again, I started work on V2. So another note about Inigo is that it's a bit different from the other APLs like Dialog APL or GNU APL. There are more symbols, and these symbols are useful for building neural networks. And also different is the fact that you can trigger differentiation and get the partial derivative of a variable, just that. So that's also part of the reason why it's not open source yet, because these things change from week to week, right? The joys of actually controlling the language. So thank you for letting me indulge in my side projects, but let's get to the meat of the talk. As I have alluded to earlier, by simply switching my programming language to APL, I changed the way I think about solving problems. And I think this is very true about anyone who's used APL. So maybe this would be a better logo or slogan for APL. This is an actual APL logo. I added the slogan. But let me show you a concrete example of how APL helps me think differently. Now, consider these three symbols. What do they do? In APL, you read them as inner product, or in NumPy, it's a dot. You'll note that there are three symbols here. plus, dot, and times. Now, we all know what plus and times do. The only difference in APL is that they also work on arrays. Here, 1, 2, 3, 4, and 1, 10, 100, and 1,000 are arrays, and when you multiply them, you're basically multiplying them element-wise. Side note, I also want to talk about reduction for a bit because it's actually important to how inner product works. Let's say you've got an array 1, 2, 3, 4, and you want to collapse this array down into one single number. What do? Well, one way you can do it is you can add up all the numbers. We call this summing. Everyone's familiar with this? 1 plus 2 plus 3 plus 4. And we write sums as plus slash in APL. And the best thing about this is if you change plus into times, you get a product, 1 times 2 times 3 times 4. And the reason why I'm introducing reduction here is because it's actually relevant to how inner product works. So let's go back to this. We know what plus and times does. What does the dot do, right? Because it's pretty magical what the dot does. And magic is not good for software development. So this is what the dot does. The dot is another function that considers the left and right function. And so it applies the right function first and takes two arrays and multiplies the results together. So you've got A times B, put them in one cell, B times E and C times F into one. And then after that, it will apply the left function. And what does it do? It collapses, reduces the array. And now you can apply this to matrices as well. So the inner products of the blue row and the yellow column would be the green, and so on and so forth. Good. Mind blown yet? I hope it doesn't blow your mind because this is how inner product works. If you know linear algebra, this is basic stuff, right? But the thing that really changes my mind is that after using this for a while, I got this Satori moment, right? Where I realized that each of these symbols are individually functions. And that means instead of plus and times, I can just replace them with any other binary function. Let me show you an example. Let's say we do an inner product of these two arrays, and the result is 70, right? Now let's replace the left function. Left function. And instead of using plus to reduce, we use concatenate to reduce. So as you reduce, you're actually recreating a new array. Right? Now we've got a new array, 5, 12, 21, and 32. Now let's replace the right function. Instead of multiplying, we're going to actually print what it's actually doing, okay? Don't worry about the syntax. This basically says take the left element and right element and concatenate them and put a multiply sign in between them as a string, right? Now we can see how the whole process of this inner product works. And if my example hasn't hit you on how powerful this thing is, let me explain it to you. I just wanted to inspect how the dot works, man. And I did it just like that, right? Having this sort of ability, having the whole function in front of you to change your existing solution, right, changes the way you solve problems. It gives you confidence in exploring. And more importantly, it also clarifies your thinking, allowing you to solve your problem in its most simplest form. Most simplest, haha. So this is Bayes' theorem in APL. C is the array of conditional probabilities, and P is the array of prior probabilities. Right? If you start with the equation in the background, I'm not sure if you can see it, and you start whittling it down, remove all the unnecessary details, you finally arrive at this function, which I think is the Bayes theorem in its simplest form. I would like to see you do that with Python. But of course, not all my code looks like this. Most of my code looks like this. And this is a function that takes a time series and finds a point in time that something happened that caused the mean of the time series to change, to shift. And that's it. That's the entire function on screen in one line. The equivalent in Python takes about 30 lines of code. And it isn't as obvious to anyone who's reading the code of what the function is doing as what you have on screen here. Now, when I say obvious, you obviously have to know how to read APL, right? So clear thinking isn't all. By virtue of having a different notation, right, I discovered or rediscovered some of these things. The second one is a bit cheeky. Let's see if I've got time to explain it. No, okay, come find me after the talk and I'll explain the second one to you. It's actually quite cute. But let's go back to problem solving for now. You may note so far that I've merely talked about my experiences with APL and how using APL changes my mind on how I solve problems. Right? I'll note that APL is not everyone's cup of tea. No one likes to type symbols. And really, at this point, it feels like I'm flexing. So let me flex a bit more. This is This is how I solve problems, right? I'm describing problem solving from a very personal point of view. I'm the kind of guy who will write small programs to scratch my itch. So for example, when I needed to annotate a bunch of text documents for a machine learning project in the previous work, instead of using external annotation tools, I simply wrote up a small Emacs library and annotated it. Who needs Protege? But that's arrogance talking, right? This solution is not scalable. For one, it's very difficult to train up external annotators to use Emacs. And even if you have a bunch of developers in-house doing annotation in-house, and there are good reasons for doing this, not all developers use Emacs. So therein lies the first tension of this talk, what we call programming in the large versus programming in the small. This concept was created in 1975, and in 2022, we're still not very good at solving it. So I want you to consider a program that is written in Spark, right? By and large, we can consider this a program in the large because it's going to run on many machines, a cluster of machines, and it's the kind of program that many people will touch, right? So the real result is that we have individual programmers who have to follow a rigid set of rules and run the clusters when they want to do and try something, right? It's quite hard to use when you compare it with immediately coding up a solution on your computer. The Spark ecosystem leaves very little room for personal sparks of creativity, which will often solve a problem in a much far superior way. So, the question is this: what do we prefer? Do we prefer to work within a rigid rule set that offers no creativity? Or do we want to work with personal flair, right? There is this notion of that Gerd Hofstadter came up with, individualistic cultures and collectivist cultures. And in the context of software development, in the context of data science and data engineering, we often have to choose a side. So what ends up happening is the data scientists will all code, with personal flair on their Jupyter notebooks, and the data engineers will come in and wrap the processors around that. That's a bit complicated, basically. The question is this: is there a way to eat your cake and have it too? And I think the answer is yes, through the use of multiple notations, which I'll discuss in a bit. But first, I want to continue on this digression on programming in the large. Russ Cox, the co-creator of the Go programming language, has been known to say that software engineering is what happens to code when you add time and other developers, other programmers. It's a riff on this quote by Titus Winters, of course. Now let me turn this question around and focus it on data engineering. What happens to your data engineering stuff when you add other programmers and time and other data scientists? So today we see many products to the tune of, oh, it's simple. We will take your Jupyter notebook, we'll wrap it up in a REST or a gRPC service, just chuck a load balancer in front of it and you're golden. That's not a problem, okay? I want to make it clear, it's not a problem, because we do live in a society that rewards fast turnaround, right? The faster you can package up stable diffusion into a product, the faster the VCs are going to come knocking on your door to give you money. But what happens when you add time and other programmers? Well, you'll end up with an ecosystem of overly complicated processes. Now everyone has to specialize a bit, and that sucks because I'm a human being, and specialization is for insects. Now, what I'm trying to say is this is not a knock on these products. I use many of these tools myself, but it's often I sit down and think, why do we really need this, right? Sure, some of these are what Fred Brooks would call essential complexity, but I would say that majority of these things are accidental complexity that comes out from not sitting down and thinking our problems through. And as data, how do we think about problems, right? As mentioned earlier, when we solve problems, we're actually establishing the rules of how the elements of the problems can interact with one another. And when there are rules and elements, we call it a language. And when that language is written down, we call that a notation. As data engineers, the elements are things like the database, the machine learning algorithm, the Jupyter notebook. Right? The rules are not whether we can add a string to an integer, but rather how we can keep our data in the correct shape and form across time and space and people. Who here hasn't dealt with, multiple sources of truth for one thing, right? People who apply data mesh without actually applying data mesh, that is. So let's go back to this Iverson bloke. Ken Iverson won the Turing Award in 1979, and in his Turing Award speech is actually called Notation as a Tool of Thought. Good notation often leads to new discoveries. For example, by simply inventing a new notation, John Conway, from the aforementioned Conway's Game of Life, he discovered a whole new zoo of knots called rational tangles. Right? Rational tangles are actually very useful in studying DNA topology. And I think I've digressed, but the point I'm trying to get at is better notation allows us to understand things better because it allows us to frame the problem differently. And in Iverson's talk, he actually noted the criteria for what passes as good notation. A good notation, according to Iverson, allows you to express your problems easily. It is suggestive of more things that you can do. It subordinates details. It doesn't take much effort to use, and you can obviously see that it is obviously correct very easily. Now, I can talk at length about each of these properties. In fact, I've talked at length about representing problems. But I want to focus on the next three things: suggestivity, subordination of detail, and economy. As you have seen when I was explaining the inner product, realization of what the dot does suddenly suggests to you that you can put any other binary functions on either side of the dot. And this is what suggestivity is. Your code suggests new code. Your solution suggests new solutions. Think about this. Are there any data engineering products out there that does this? Now, let's talk about subordination of detail, right? I think it's pretty given in modern-day programming that abstraction is a good thing, up to a certain point, that is. I've read a bunch of writings from Iverson, and I'm convinced that he's actually one of those few people who knows the difference between abstraction, aggregation, and agglomeration. The differences between these three things are very subtle. They all sort of mean taking many things and making one thing out of each other. So let me give you a sort of 1-minute version that won't really do it much justice. Abstraction is basically hiding your things under a name. And if you come from the lambda calculus school of computer science, your basic form of abstraction is wrapping things in a function. If you come from the Java school of computer science, then you've got more ways of abstracting things. You can use interfaces, you can use subclasses, and so on and so forth. Right? Aggregation is basically the same thing, but you get rid of the underlying details. When I talk about the average height of all Australians, I don't actually mean every single human being. I've forgotten about them. I only talk about the average height. And lastly, agglomeration is basically referring to a collection of things, and you always refer to the collection of things. And that is what subordination of detail is. When you write inner products in APL, you always write the same three symbols. You don't write np.dot as you would in NumPy. That's abstraction. And subordination of detail is actually a very useful tool. Imagine if you can have the whole function in front of you every time you try to solve a problem. How would that change the way you solve problems, right? Now let's talk about economy. Earlier when I gave the Spark example, there was an example of a lack of economy. To do things with Spark is generally very hard. You've got to do so many other things just to change one small thing. I also mentioned earlier that with the Einstein summation thing, that it works mostly on pen and paper because working with equations on computers is not that great. And when you work with Maple, for example, it doesn't give you that sense of manipulation that you have with pen and paper, right? So when I said writing engages your brain in systems 2 thinking, it comes with caveat. You need to be able to manipulate your thoughts efficiently and quickly enough, right? If you're bogged down trying to get your thoughts into the medium, into the computer, into the paper, by the time you come to manipulate them, your ideas would have already evaporated. So for a lot of things, pen and paper still rule supreme. But having to transfer that writings on pen and paper to a computer would mean that you will need a different set of notation for your computer. And this ties in very neatly to a principled statement I want to make. There is no one notation to rule them all. Like it or not, we use multiple languages and multiple notation all the time, every time, and in more contexts than you can ever imagine. So I'm going to quickly enumerate through them, but the easiest example would be specification and implementation languages. In many other words, is the type language and the term language, right? So in languages like Go, it's not very obvious that you're writing in two different sets of languages, when you're writing things like function signature. But if you use languages like Idris or Haskell, it is very obvious that you're working with types as one language and working on the terms as another language. And sometimes of these specification and implementation language, only one of them actually makes it out into the medium. Take JavaScript, for example. The types are still there. It's just stuck in the head of the programmer, right? You don't write the types, but it's stuck in the head of the programmer. And because every programmer thinks differently about types and thinks differently about the programs, what you have is you have 1,000 different type languages, essentially, for every programmer that touches the same JavaScript program. Another clear example is when we need to work across different computational models, right? We drop down to writing regular expressions all the time, and when we need something databasey, we write SQL. In these two examples, regular expression and SQL, it's very clear that you're writing in a different notation. But equally, what I want to point out is that if you use things like LINQ or SQL Alchemy or Snowpark, you're working with the same language written differently. Think about that. Your df.groupby is exactly the same as SQL, but it's written differently. Okay? And this is something I'll talk about in the next few minutes. The third way that we can use multiple notation is in hierarchical use, right? So Naughty Dog, a game developer of Last of Us, had developed a new programming language called Go, which is a Lisp, and it works as a scripting language over the core, which was written in C++. And if you're interested in Go, by the way, there's opengo.dev, which tries to reverse engineer Go, and that's pretty cool. There are other ways of using multiple notations and multiple languages. Come find me after the talk if you want to know more. The point I'm trying to make is that we do use multiple languages and multiple notations all the time, at the same time, by the way. And this is useful, right? Who here likes to solve problems on Project Euler or LeetCode, I guess? No? Okay, so one of the funnest things that you can do with Project Euler and LeetCode is that you can solve the same problem multiple times with different languages. And when you do so, more often than not, you end up seeing the problem in a different light. And I like to call this binocular vision. Each of our eyes take the scene in front of us and see a different, slightly offset and different planar projection of the scene in front of us. And when you put them together, you actually see the scene in front of you with greater fidelity. So now we can ask, what are the properties of good notation, right? When you want to talk about good notation. Here I listed 3: interrupt, fit for purpose, and that they're distinctive. Data engineering products, by and large, fail all 3. This is because, as a community, we somehow stuck with the mindset that there should be one notation to rule them all. And this is rather backwards. We want one environment, multiple languages. What ends up happening is one language, multiple environments. Right? We don't want that. And the cynical version of me would say, we end up with that because, environment capture is richly rewarded by investors. I'm just being cynical, right? But let's talk about an interop. When I say interop, I don't mean, let's just all use gRPC. And that's one form of interop, but what I want to talk about is interop in form of writing. The gold standard for interop is when you write arithmetic expressions in most programming languages. You just write them. You don't realize that you're dealing with a completely different language, right? So this is a very well-integrated example. But there's another language that does not have numbers or plus or minus built into the language, lambda calculus, for example. All right? This is how you would write 1 + 1 in the pure lambda calculus with church-encoded numbers. Right? Let me ask you this. Would you want to write this on a day-to-day basis? No, you would prefer to write the first one, right? So with this that has a high bar and a low bar, I want you to consider the tools and languages that you use for your everyday work. Where on the scale does it fit? It most likely fits somewhere in the middle. And we often have to import libraries to use another language, basically. And that's okay. But if that's the pinnacle of human design programming languages, I would be very, very sad. And yes, to the lone lisper at the back of the room, I hear you, mate. But I think there are better things like tree calculus in the future. So let's go back to properties of good notation, shall we? Here are the reminders. We've talked about interrupt. Now let's talk about fit for purpose, right? How do you know that your notation is fit for purpose? Well, to misquote Einstein, it should be as simple as possible and no simpler. So contra program, we should not be using the most powerful language. We should be using the least powerful language. You should not be using a Turing-complete language, right, to match a string that's written in a regular language. Use a regular expressions engine. And fortunately, most programming languages nowadays do actually have a regular expressions engine built in, so the process is quite smooth. Oops, sorry. So let me ask you this, right? What about ETL and the other things that data engineers do, right? A very common thing that we do nowadays is to have microservices. And we would describe our operations written in YAML, and we submit them to the microservice or product. and they will pass the YAML and do the thing and then pass it on down the pipeline, right? The notation used is universal, it's YAML. But more often than not, it's not fit for purpose. And that's why we have to come up with hacks like templates and YAML. You guys know what I'm talking about, right? Cool. So the last property of good notations is that the notations are distinctive. What I mean by that is when you're working in one language and then you move to a different language, you will know that you're working in a different language. I know I cannot be the only one who gets stuck in piles of CloudFormation with YAML just to get that bloody SageMaker to do the thing I want to do, right? So when you have layers and layers of non-distinctive language, you're going to have A, be in trouble, or B, you're just creating another reason for that, a new startup to exist in that ecosystem picture I showed earlier. Now, so far, the things I've been saying have been very abstract and pretty far from what data engineers do. So let's bring this back a bit. What exactly are my recommendations, right? The tools exist in the market, but they're not the things I prefer to use, but I accept that they exist, and I would use them. Instead, we can focus on the process of solving problems. I want you to take away from this talk the way I framed problem solving. I want you to think about how language is used to constrain a problem space. Now, think about how you can enable your team to work with individual flair and yet cohesively as a whole organism. Now, I want to impress upon you that the solutions that we have today are pretty damn terrible, right? So I want you to go and invent specific languages for your specific problems. I want you to solve your problem multiple times with multiple languages, and then take a step back, right? I want you to then look at it. How are they different from one another? How are your solutions similar to one another, right? Study what unifies the difference, because that's the core of your problem. Solve that, okay? And if you do that, you also reduce the cognitive load that may exist when you have 1,000 languages blooming. Now, and while I won't give you specific recommendations like use Lisp, use Go, rewrite in Rust, I will give you some alternatives that you can take right now, because there are simply other options that are far superior to what we have in industry. Instead of using YAML for all the things, death to YAML, we should split up our notation. For configuration stuff, use Q, use DAO, right? These languages have an excellent verification mechanisms for their grammar. And for your data language, instead of using JSON and having to validate with the JSON types, whatever, use protobuf, right? If you have a process that ingests raw data and put them in some sort of structured SQL-like thing, use DBT so that you can verify that the data fits into a particular schema, right? Use Malloy to break things down into smaller parts that you can look at it and say, okay, this is obviously correct. That way you can manually verify your modules. And all these things, by the way, fall into a class of what Gary Miller calls deterministic name algebra. And if you're a language nerd like me, this is actually a pretty exciting space to be. So now we've come to the end of the talk. And what I want to impress upon you is this, right? Language is the structure of rules and elements of a system. We solve problems by establishing the rules and finding out what exactly are the elements of the problem. In short, we use language to solve problems. When we write language down, we call that notation, and it's used to manipulate terms of the language. And I've given you 3 examples of how changing the notation changes the way we look at a problem. You've got Einstein's notation, making neural networks faster. You've got Conway's notation, discovering a whole new zoo of things. And APL, changing the way you think about programming. What I'm trying to say is that we should use more diverse forms of notation to solve our problems. But in modern-day data engineering tasks, we're sort of stuck on one universal notation. And this is making a lot of our problems harder to solve because it makes it more difficult for us to think through our problems, right? And we are also creating accidental complexity. So, ironically, to make things simpler, we shall endeavor to use specific languages for specific problems. And it may seem a lot, but it makes the overall system a lot easier to understand. With that, thank you for listening to this weird guy giving a rant. Thank you to those people who have peer-reviewed my slides, this talk, and most importantly, thank you to the organizers and you for actually having to sit through all of that. Thank you.